Hello students, welcome back to the another session of our data structure journey. We are already completed all the topics related to the linear search, linear data structure and searching also we are cover how to search an element, how to insert the data, how to delete the data, how to update the data. Linear search we are completed. Now we are doing the non-linear data structure like the graph and tree. We are already cover what is a tree, what is the types of tree, what is the binary. Next category we have to cover that is the binary search tree. So first we have to know what is a binary search tree. Binary search tree is a non-linear because the data structure, our main objective, how to store the data so that we can retrieve the data efficiently. For example, we want to store the information related a folder. Inside the folder subdirectory, inside the directory subdirect folder, inside the folder files are present. So how we are going to store? We cannot store this information regarding the directory folder in case by help of the array linked list or by help of the stack queue. We cannot able to perform the operation. We need some hierarchical structure where we can able to store the information related to the directory or to the folder. So for that, we go for the nonlinear data structure. So one type of nonlinear data structure we called as the tree, where we are store the data in a sorted manner. Each node in a binary tree stores some information. Binary tree means it can store the binary search tree is a one type of binary tree. Binary means it can store maximum two children. So two children, so the two children we classify in the left children as well as the right children. Binary search tree is a one type of specific type of search tree where the left child always store the value less than the parent child and the right child always store the value more than the or greater than the parent node. So this main objective of this type of data structure is that by help of the storing such a way that the left child store the less than or equal to data value than the parent and right child store the value greater than the parent value is main objective. We can able to perform insertion, deletion and searching element very efficient way. That is the main objective. Let us take in this example. As we know, topmost element we called as the root. So 40 is the root child. Now, from the 40, what are the subtrees? 30, 25, 35. Now, 30, 25, 35 all are less than the 40. Same concept is applicable to this node, this subtree. 30, 30 left child is 25 and right side is 35. So, right side value is greater than the parent and left child is the less than the parent child. Similarly, if we move to this one, 50, 50 is greater than the 40. Now 40 left child, 50 left child is 45. 45 is less than the 50 and right child of the 50 is 60. So 60 is greater than the 50. So here what happened? Each and every node we cannot say only the root node. No, no. Each and every parent have the left child less than the value and right child greater than the its parent value. This is the applicable for each and every node present inside the tree. So next question, how we can able to construct a binary tree? If the data or elements or information is given, how we can able to construct a binary tree so that the left child always contains the less value or equal to the parent value or right child store the value of greater than the parent child. So let us consider this is an example is given. Data we are going to store 50, 25, 65, 45, 90, 60, 70, 66, 55, 27. So these are the data we have to store. How to store? We have to store by help of the binary search tree. So what happened? First element. So first element, which element? 50. So 50 we have to consider as a root. Then we have to traverse from left to right. We have to traverse left to right and make each and every node as a to store as a next node and we insert in the proper means first element we consider as a 50. Then so we consider the 50. After that, what happened? Next value is 25. So 50 we make as a root. Then which element? Next element is the 55. So next element 55 means what? 50, sorry, next element is the 25. 25 is less than or greater than, less than the 50. If 25 is the less than means it will becomes to a subtree. So now 25 becomes the left subtree. Then next element is the 65. So 65 is greater than 55, 50, so it will come to the right child. Next element 45. So whenever we go to 45, anyhow we have to traverse from the root. 45, this is 50. 50 means 45 is less than, so it will come to this child, left child. Left child is 25. So now 45 is greater than. So greater than means it will becomes the right child of the 25. Now it's become the right child of the 25. Next element is the 90. So we have to traverse from the root. So 90 means we have to traverse 90. 90 is greater than the 50. So it will come to the right subtree. So right child means 65. Now 65 is less than the 90 means 90 will be placed in the right side. So right side it will place. So right side it will place and become the right child. Then next element 60. So whenever 60, 50. So 50 is less than the 60. So it will come to right child. Now 65. 60 is less than the 65. So now it becomes to the left child of this one. So it becomes the left child. Then 70. So next value is the 70. So we have to anyhow we have to traverse from the root to proper position. So 70 means 70 is greater than 50. So it will come to the right child. So 65, 70 is greater than the 65. So it will come move to the right node. So right node is the 90. 90, 70 is less than the 90 means it will becomes to the left child. So it will becomes to the left child. Then 66. So 66 we have to traverse from the root. So 55, 66 is greater than. So it will come to the right side. Now 65, 66. Anyhow 66 is greater. So we have to move to the right side. So right side means 90, 90 less than. 66 less than. So it will come to the left hand side. Now 70, 70, 66 is less than. So it becomes to the left child. Then next element is the 55. 55, so we have to start from the root 50. 55 is greater than the 50, so we have to move to the right side. Now 65. 55 is less than 65, so we have to move to the right side. 60. 55 is less than 60, so now 55 will be left child of the 60. It's done. Last element, that the 27. Now this is our root, that is the 50. So 27 is less than the 50, so it moves to the left side, left node. Left subtree is 25 is the root. 27 is greater than, so it moves to the right side. 45 is present, 45. Now 27, 27 is less than the 45, so it will becomes to the left child. So now our binary search tree is completed. If we check each and 50, 50, all the elements 25, 45, all are less than the 50 value, root value. Right side, all the elements are greater than 50. All the elements. If we take this one means 90. All the left subtree is less than 9. If we consider this root, 65. 60, 55 less than, so all are left subtree, right subtree is 90, 70, 66. So it will be satisfy the condition for the binary search tree. So this is a simple way how we can able to construct the binary tree. Let us take another example here. Elements are given. First element is the 10. So 10 element means we have to consider 10 as a root. So we make the 10 as a root node. So we make the 10 as a root node. Then 5. 5 is less than the 10, so it will be becomes the left child. Then 45. 45 means we have to from the root. 45 is greater than the 10, so it will become the right subtree. Then 30. So anyhow, we have to traverse from the root. Root is 10. So now this is 45. 35 is less than the 45. Sorry, 30. So it becomes the left subtree. So left child, it becomes the left child. Now 4. So this is root is 10. 4 is less than 10. So it will become to the left child. Now this is 5. 5 is more than 4. Means it now 4 becomes the left child. Next element is the 8. 8 means what? We have to start from the root 10. 8 is less than. So left child. 5 greater than. So it becomes the right child. Next element is the 14. 14 means root is 10. So 14 means greater than the value 10. So it will move to the right child. Now here 45 is present. 45 is greater than the 14. So it moves to the left sub. So 30, 14 is less than the 30. Less than means left side. So left side we make the 14 now 56. So this is 10. 56 greater than 10. So we move to the right child, right side node. Then 45. Our element 56. So 56 is bigger than the 45. So it becomes the right child right now. Then 75. 75 is greater than 10. So right side we have to move 45. Then 75 greater than the 45. Then again we have to move the 56. 56 is then 75 is greater than. So we have to make the connection here. Then 80. So anyhow we have to traverse from the root to the specific position. Then only we can insert the node. So 80 means greater than 10 left right child, greater than 45 right child, greater than 56 right child, greater than 75. So now there is no left right side, so we have to simple put the new node. Then 40, we have to start from the root. 40 is greater than 10, so we have to move to the right side node 45. 40 is less than, so we have to move to left side 30. 40 is greater than, so it means greater than means right hand side we have to insert. Next value 65. 65 is 10, 45, so 35. So we have to put inside this one. Last element 70. 70 means we have to try 70 is greater than 10, greater than 45, greater than 56, greater than the 75. Then less than 80. So less than 80 means subtree, left subtree. Because 70 means it is less than 75 means move to this node. Move to this node. Then it is greater than the 65. That's why it is 70 here. So next one, what are the basic operation we can perform in a binary search tree? First one is the insert, means we want to insert an element into our tree. Second one is the delete. In case of binary search tree, the create of binary search tree we can treat as a insert an element into the tree. Then here only one difference in case of the tree is that previously whatever the data structure we covered, that is the array, stack, queue, linked list. Traversing means the first to last element. But in case of tree, we are performing the traversing three way. First one is the pre-order, in-order, post-order. So there are three category of the traversal of a tree can be possible. Then searching an element in the tree. So this is the basic operation. Next one, how structure node has consist of three elements. First one is the data. We want to store the information. Second one is a pointer to the next node. Next node or previous node, that is the we represent in a double linked list. But here what happened? One pointer points to the left child, another pointer points to the right child. Here, if you declare the structure node, node is the name of the structure we want. If you make a node, then you have to write down. If I make the structure of a tree, then what happens? Structure tree left pointer, structure tree, left pointer. So this is the way we have to declare the node. So now what happened? We have to insert the data into the binary search tree. So inserted data is the binary search tree is the same as the operation is how to create the binary search tree. It's the same. It is not going to be any way big difference. It's the same. It is not that much difficult. So if the tree is empty, insert the first element as a root node. So right now what happened? Tree is empty. So what is the first node? First node is the 10. So we make the 10 as a root node. Next element 5. If the root is empty, no, it is not empty, then next line. If an element is less than the root value, it is added to the left subtree as a leaf node. Now 5 is less than 10, so we have to make the 5 as a left subtree, left sub child or subtree we can call as. If an next element 20. If a tree is empty, no. If an element is less than, no. If an element is greater than the root, then add to the right subtree as a leaf node. So now 20. So 20 is greater than 10, so we have to make the 20 as a leaf node or child or a subtree. Next element 15. So 15 means it is greater than 10. So it will move to the right side. As a leaf node means again this node we have to consider as a root. So 15 means it is less than the 20. So it is 15. Next element is 45. So 45 is greater than 10. So right side we have to move. This is 45. So 20. So this is 45 because 45 is greater than the 20. Next element 25. 25 means it is the right now. Just remember before that we just cover how to create a binary search tree. To create a binary search tree is same as the insert the data into the binary search tree. Little bit same, not 100% same because here we're starting from one node. So now 25 is given. So 25 means it is greater than 10, it is greater than 20, but less than the 45. So we make the 25 as a left side of the 45. Then 30. 30 means greater than 10, greater than 20. 30 is less than 45, but it is greater than the 25. So we make this as 30. Then 55. 55 means what? 10. We have to traverse from 10. It is greater than 10, greater than 20, greater than 45. So it becomes the right child of 45. Then 75. Greater than 10, greater than 20, greater than 40, greater than 55, greater than. So it will be added at the right child of the 55. Then 40. 40 is greater than 10, greater than 20, but less than 45. So it will come to this side, 25. It is greater than 25, so it will come to 30. Then again it is 40. So now here what happened? It becomes the 40. So one by one we insert the data. So here insertion of how many elements? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is the way we can insert the data. So next one is how to delete an element from a binary search tree. So there are three cases. If the root is the leaf node, simple, we have to remove the node directly. If the node has one child, then copy the child to the node to be deleted and delete the node. If the node have two children, then find the in-order successor of the node and copy the content of in-order successor to the be deleted value. So let's take an first cases if it is a leaf node. For example, we have to delete either 15, 20 or 35. For example, we want to delete the 20. So delete the 15. So delete the 15 means there is no subtree. So simple, we can delete this one. On simple, we go for delete this one. So information is deleted. So it is very easy. If it is the no, if the deleted node is a leaf node, then simple we can delete this one. Case 2. If the node has a single child, so here what happened? 25 is a single child, 28 is a single child, 25 and 40 has single side. So if we have to delete 25 or 40, then what happened? We have to copy the deleted value to the remaining value. For example, I want to delete the which value? 40 we want to delete. If you want to delete, then what? And simple copy the 35 value to this one. So here what happened? We copy the 35 value into this one and delete this node. So you have, if we copy this one and delete the value, so there is no loss of information. We copy the value and delete the value. There is, and whatever the after deletion, each and every operation you have to check whether the it satisfies the binary search tree or not. Yes, right now it satisfies that. Next one is if the node has two children. So now, for example, we want to delete this one 30. Two children, 28, 35. Then what happen? Find the in order successor. So which one is the in order successor? 35. So copy the 35 to this node, that node 35, and release the memory occupy the. Now, after deletion, we have to check whether it satisfies the condition of binary search tree. All the node left hand side is the less than and right side is the greater than. Yes, it is satisfy the condition. So if it satisfy the condition means after the deletion, our operation does not lose any information. Next next algorithm is the binary search algorithm. So for example, this is the data is given to us. After that, we have to search the element. So data is given to us, tree is given to us. We want to search the element. So if we go for searching 40 elements, then what happened? We have to traverse the route. 40 is greater than, so we have to traverse this one. 40 is less than 45, so we have to left subtree. Then 40 is greater than 30, so right subtree. So if whenever we move to the right, yeah, we found that the 40 is present. So output will be present, that is the present. Yes. Next one searching value is the 25. So 25 means greater than the 10, so it will move to the right subtree. Then 45, 25 is less than the 45, so it moves to the left subtree. Then 30. So 30 means 25 is less than, so it will search to the left side. Now 40 is the leaf, 14 is the leaf node, and 14 is not matched with 25. So we make that key is not found, our searching is unsuccessful. So means the element is not present inside the. Next one, in case of binary search tree, we know how to traverse the tree. So first we have to traverse the pre-order. So pre-order traverse means visit the route, then print the data, then traverse the left subtree. Remember here, whenever we go for left subtree, we have to recursively use the traversing. So right subtree also we have to perform the recursively. So for example, this is the data is given. We have to go for the pre-order. Pre-order means first what is the value root. So we print the value for 50. Then traverse the left subtree. So this one, so for this subtree, what is the root value? 25. So first we have to visit the root. Then after that we have to visit the left subtree. Left subtree is which one? 20. Anyhow, we have to print the root first, then 20. After 20, there is no left subtree. So for 25, what happened? Left subtree is already completed. Then we have to move to the right. Right means 45, 27. So whenever we go 47 at that time, what happened? First visit the root. So visit the root means 45 is the root. So we have to write down the 45. Once the root is visited, then we have to go to the left. So left means 27. 27 itself is a root or not? So we have to write down 27. There is no left subtree as well as no right subtree. So for this one, for 25, this subtree is over. Now, once this subtree is over, then we have to move to this subtree. So for this subtree, what we have to do? 65 is the root node. So what we have to write down? That is 65. So 65 is the root node. Then we have to go to the left. Whenever we go to the left, 60 is the root. So we have to first write down the 60. Then it will move to the 55. 55 is the root node. Then left sub is 50. Nothing is there. 60 left is already over. 65 left is over. Then what happened? It has to go to the right subtree. Right subtree means 90. Anyhow, it is a pre-order. First we have to visit the root, then left subtree and 70, then 66. Left subtree means 70 is the root, then 66 is the root. Then 66 is the. So once the root and left subtree is bigger, what is the remaining? Remaining is the 100. So this is the pre-order traverse of a binary search tree. Next one is the post traversal. Post traversal means first the left subtree, then the right subtree, then only the root. So pre, post and in order depend upon the root position. So here what happened? First left subtree, right subtree, then only it will. So anyhow we have to start from the root 50. We have to traverse the left subtree this one, then 25, then 20. So after that what happened? 20. There is no subtree, so 20 is the. We have to print visit the root after left right. Here there is no left, not right, so it will print. So now for 25, the right we have to move 45 for 27. So which one is the present? So 27, then 45. So left subtree, right subtree is over. Once it is over, then we have to print the 25. So for left subtree of 50 is over, then we have to go to the right. 65, left is 60, then 55. So after 25, we have to write down the 55, then 60, left is over, then we have to go to the right, means 90. 90 means we have to go to the left subtree, then only the right. Left means 70, then 66. So here what happened? After 60, we have to write down the 66, then 70, right subtree, then what happened? Then we have to write down the 100 because right subtree, then the root is going to be print that the net. So this one is over, this one is over, then 65. Then the left subtree visited, right subtrees were visited. Then what happened? 50 we have to write down. So this is the way we can traverse the binary search tree in a post order manner. So first in order value is the 20, then 25 because after left we have to go to the root. So 25 is right now to then right. Right means 45, then 27. So anyhow to first we have to visit the left, that is the 27. Then 45, there is no right. So for this one, left is over, right is over. Now, this one is over, this 45 is over. Then we have to go for the 50. So now 50 is left, then we have to move to the right. So this is the left, this is the left. So first we have to visit the left. After 50, what happened? 55, then 60. In order means after the left means the root can be printed, so we have to write down after 60, 65. Then we have to move this one, this one, this one. So now 66, then 70, then 90, then 100. So this is the way data can be present. So what is the advantage of in order? If you traverse the binary search tree in order traverse, you got the value of is the sorted 20, 25, 27, 45, 50, 50, 60, 65, 66, 70, 90, 100. So this is the way we can represent the tree by traversing either pre-order, post-order, or in-order. So three order we can able to do. Only it is depend upon the which place the root is present. So searching operation is very easy compared to the linear search. The alignment of best flavor is the range queries which is executed various of value existing between two key. This helps the database management system. So we can use the binary search tree for this purpose. Disadvantage. The main our disadvantage is that all the node has greater than or less than the root of the tree become the screw and simply but put the tree becomes slant into one side of the computer. So this is the there is chances. So for that, what happens the time complexity is the order of n because the traversing is the not that much easy for to insert the value. So overcome this issue of skewness of the binary search tree, the concept balanced binary tree was introduced. So upcoming video will cover the balanced binary tree, that is the AVL tree. We will cover how to balance. Otherwise, what happened? The tree becomes to be a screw, either left screw or right screw. Thanks for watching the video. Hope you are able to understand the concept of binary search tree. So next video will cover the implementation of the binary search tree using the C language. Please subscribe the channel, like the channel as well as the share the channel. Thank you so much.